Okay, just a quick comment on one of the homework problems. This is adapted from a homework problem. The homework problem I had assigned to you here. I want you to try your integration by parts and see if you can integrate what you get. But when you do this, it's first order linear and it's non-homogeneous. So this is what we have. We use this integrating factor as we've seen, so this is nothing new. And when we do the integrating factor, we multiply both sides by the integrating factor. We get this. We verify that this side is just y times your integrating factor prime. In other words, the derivative of y times your integrating factor. It'll always happen for first order equations, okay? If big P is the antiderivative of this thing, which we've notated by little p, you're always going to have the integrating. The integrating factor is always going to make your left-hand side into the derivative of y e to that integrating factor. Always. You can prove that in general. But I've asked you to work it out for several examples. Okay, so, and then on the right-hand side, you get this. And it's also what it looks like. We've got a cosine t, e to the sine t to the cosine t. If it confused me, it's going to confuse probably nobody else. Nobody looks at things the way I do. Okay. Now, if the derivative with respect to t, and of course this is implicitly with respect to t, if the derivative of this with respect to t equals this, then this has to equal antiderivative of this thing. Okay? Some antiderivative. A general antiderivative with an integrating constant, an integration constant. Okay, so you do this and you see that this thing leads to a very simple U substitution. Now the problem I gave you for homework, you had a sign here, so you ended up with a sign here, and no simple substitution is going to do that. So it's natural to go to integration by parts and see if you can do it that way. Okay? Anyhow, I'm doing this problem because it's easy to integrate. And then you see what the solutions look like. It's always going to turn out pretty much the same. You're going to get a y times your integrating factor equals whatever you get when you integrate this thing plus a constant. So when you solve for y, you're going to be dividing by that integrating factor. And you got two terms here, so you're going to get this over the integrating factor, which in this case will give you 1. This just is the integrating factor. And that's just a coincidence of the functions and the way the integration came out. That will not generally happen. And then you got your constant times the reciprocal of your integrating factor. Now instead of writing that e to the sine t in the denominator, I wrote an e to the negative sine t. Okay? Now you can think about what the graph of e to the negative sine t would look like. Okay? You might or might not be able to reason that out. If you know how to take the graph of a function and then do the graph, it's composite with another function, then you can do it graphically, and I encourage you to be able to do that. It's a very useful skill. It's kind of tough, okay? And maybe you're not going to do it. Maybe you're just going to go to the local crutch, your calculator, and look at what the graph looks like, but you should reason it out before you do that. You should at least understand that when sine t is 0, what's going to happen?
It's going to equal 1.
Yeah, so you're going to get 1 plus c, right? Whatever that is. And when the sine t is 1, you get c e to the negative 1. Well, what's e to the negative 1? It's about 0.37. Yeah, a little less than 0.4. Okay? And you should kind of know that because it comes up. Okay? Now it's not difficult to figure it out. E is almost 3. The reciprocal of 3 is 0.33. 2.7 is pretty close to E. It's about 10% less than 3, right? Which means that the reciprocal is going to be about 10% more than 3. Not exactly, but about. Okay? And that's a handy shortcut for thinking about things without having to punch a calculator and get something you don't understand. Okay? So we do this. Anyhow, we just use a little basic arithmetic and basic algebra 1 with some of these values, right? So sine t is going to run from -1 to 1, right? If it's 1, then e to the negative sine t. If it's -1, sorry, then e to the negative sine t would be e, right? So this number here runs from like 0.4, 0.37 something, to, and 0.37 is 10% more than 0.33 is 3.66. And it's a little more than that because the way the reciprocal works, and so 0.37 is a safe bet. That's not, I didn't do anything astounding to get that. I used grade school arithmetic with just a little algebra 1. In the rest of the world, this is grade school arithmetic.
Yeah. You were only off by 1,000.
Yeah, well, that's just luck. Okay? I knew it was going to be pretty close to 0.37 because of the way reciprocals work and stuff, but, I didn't think it would necessarily be that close. Okay? I figured it out once, checked it out, and said, yeah, for once I did something right. So I just kind of remember that. Okay? But you just start with e is close to 3. So reciprocal of e is close to 0.33. E's a little less than 3, reciprocal is a little more than that. Okay? It's only 10% less, so it's about 10% more. Those are easy things to do. 10% is an easy number. Okay? And you really want to be able to do at least that much. Okay, doing more sophisticated mental stuff, well, I'm not Richard Feynman.
He could really do it in his head.
Yeah, but the things he could do, I could understand if I was just a little smarter or had a little more working memory and had a little quicker brain.
He was a really interesting guy.
Huh?
He was a really interesting guy.
Yeah. Anyhow, I mean, and he was, when I was, well, never mind. But he was still, teaching at Berkeley when I was an undergraduate. He kept wanting me to come be in his class, but I refused. He didn't deserve that. That's another tall tale. Okay. We did use one of his textbooks, one of his Feynman series as a textbook in one of our courses. That's as close as I came to being taught by Feynman. As close as I needed to get. Okay. So anyhow, we've got this, right? So, we can get a sense of what this graph is going to look like. Everything I've told you gives you all the hints you need. You don't need to go to that infernal machine and bypass the thinking process to see what this graph looks like. Okay, it's not that complicated. It seems a little complicated to you. Okay? It's not totally trivial to me. So, it's going to be a little complicated when you're first getting into this. But it's not that complicated. There's no step in there that you can't easily do. And there aren't that many steps. And your working memory is better than mine. So you could easily enough do it. Okay, well, end of that, but I encourage you to do that. Okay, now, just looking at the direction field, we drew out the direction field. It's fairly easy, when y is 0, you just got cosine t. And cosine t is periodic, a period of 2 pi, so there's no point in looking at any interval besides 0 to 2 pi. Because it's going to look exactly the same in the next interval and the next, and then back this way too. Just keep taking this picture and slapping it down, slapping it down over here, and you get the whole picture. So you see the periodicity, whatever the curves look like, you're going to have this kind of periodicity in your solution, right? Okay? Now it's not totally clear from this picture how it develops, but I want you to develop the picture into something where you can kind of see it. Okay? So I'm probably going to put that in the assignment. I'm going to ask you to fill in a couple more points in between and maybe, halfway point here and, make this use intervals of 1/2 for your y's, up, just from 0 to 2, -2 to 2 will give you enough, okay? And then an interval like pi over 4, or even maybe pi over 3, or pi over 6 for your t values, okay? And think unit circle. You didn't instantly think unit circle when I asked you some questions here. You want to visualize that unit circle, know that the cosine is the x-coordinate, and then just where are you in the unit circle, and so forth. Incidentally, I've got a clock coming tomorrow that you'll love. No, actually, it's not the clock. I ordered a different clock because the one that I really wanted to order was a unit circle clock with pi over 6 and pi over 4 and pi over 3 and the square root of 3 over 2, 1/2 points and stuff like that. And I'm probably going to order that too, but I just ordered one that works because I want a second hand. It's just like the one I've got over there that you've probably seen. Okay, well, the unit circle clock, though, I got to look at the dimensions of it to make sure it's kind of visible from where you're sitting. And reviews say that the mechanism doesn't work very well. I wanted one of the mechanism worked because I want a second hand because that one died. Lasted a few years. Okay. Now, digressing all over the place, but you want to be able to follow this direction field and reconcile what you get when you put different points in there with what you get here. Okay?
That's always going to be a positive result, right?
What positive?
Why?
No, because C doesn't have to be positive. And think about it. I could start from down here, right?
Yeah.
If I start from down here, I'm certainly going to get negative y values, right? I mean, I'm starting with a negative y value. So C is going to have to be negative. Okay? I want you to look at this equation, this picture. Okay? Give you a better sense of everything we've been talking about. Okay. Now I want to move ahead a little bit to another type of equation that we haven't yet talked about. An exact equation. Now this is going to look initially just like what I just did here. It's basically some function. I don't want to use f because we kind of use that in classifying functions. I'll use a capital F. And I'm the primes. The differential of f of t y equals c. Sorry, equals 0. Okay? This is an exact equation, and it has this very simple solution. If the differential is 0, then it's got to be constant, right? So if f of ty is something you can solve for y, you've got your solution. Okay? Unfortunately, the equation doesn't look like this when you see it. I mean, if it does, you're pretty much done. Okay? The equation doesn't necessarily look like this. So, example. Okay? I can write just about any function of t and y, and I'll be able to develop my exact equation. So, what's your exact equation? It's df equals 0. Okay? Now it's f of ty, but you know, just writing it briefly. Well, again, you're not going to see it in this form. What's df? Partial f with respect to y, right? Plus partial f with respect to d dt, to t, dt. That equals 0, right? What's the partial of f with respect to y? Cosine t, right? What's partial f with respect to t?
Yt.
Negative y sine t plus 2t. Okay? So, what's dy dt equal to? Well, you can treat dy and dt as algebraic quantities, although you got to prove that that works for something like this, okay? But treating dy and dt as algebraic quantities, you just put this term over here and then divide this by the negative of this, basically, okay? Does that make sense?
Can we do that?
Huh?
So we treat it as a separable equation?
Oh, it's not separable. We get dy, well, okay, let's work out the details. You get cosine t dy equals y sine t minus 2t dt, right? So that cosine t dy over y sine t minus 2t dt equals 0, right? And now there's something I really don't like about what I'm saying. So I'm going to turn the tape off here and figure out what I just did.